In this lecture, I want to describe the agrochemical processes of the biomass energy generation, the fuel extraction process, and the biodiesel and the esterification processes. The liquid biofuels. The biofuels are produced in processes that convert the biomass into more useful intermediate forms of the energy. There is particular interest in converting the solid biomass into the liquids which have the potential to replace the petroleum-based fuels used in the transportation sector. However, adapting the liquid biofuels to our present day, the fuel infrastructure and the engine technology has proven to be non-trivial. Only the well-producing plants such as the soybeans, palm oil trees and the oil seeds like rapeseed can produce the compounds similar to the hydrocarbon petroleum products and have been used to replace the small amounts of diesel. This biodiesel has been marketed in Europe and to a lesser extent in the US, but it requires the substantial subsidies to compete with the diesel. Another family of the petroleum-like liquid fuel that is produced from the gasified biomass is a class of synthesized hydrocarbons called the Fischer-Tropsch FT liquids. The process synthesizes hydrocarbon fuel C10 to C12 hydrocarbons, that is called kerosene, or the C3 to C4 hydrocarbons, that is called the LPG, from the carbon monoxide and the hydrogen gas over the iron or the cobalt catalyst. The FT liquids can be used as a sulfur-free diesel or the blended with the existing diesel to reduce the emissions and environmental advantage, but it has yet to be produced efficiently and economically on a large scale, and the research and development R&D efforts are ongoing. In addition to use as an automotive fuel, FT liquids can potentially be used as a more efficient, cleaner cooking fuel than traditional wood fuels from which it is synthesized. Other alternative biofuels to the petroleum-based fuels are alcohols produced from biomass, which can replace the gasoline or kerosene. The most widely produced today is ethanol from the fermentation of the biomass. In industrialized countries, ethanol is most commonly produced from the food crops like corn, while in the developing world it is produced from the sugarcane. Its most prevalent use is as a gasoline fuel additive to the boost octane levels or to reduce the dependence on the imported fossil fuels. Two other potential transportation biofuels are methanol and the hydrogen. They are both produced via the biomass gasification and may be used in the future fuel cell. While the ethanol production from the maize or the sugarcane, both the agricultural crops, has become widespread and occasionally successful, it can suffer from commodity price fluctuation relative to the fuel market. Consequently, the production of the ethanol from the lignocellulosic biomass is being given serious attention. In particular, it is thought that the enzymatic hydrolysis of the lignocellulosic biomass will open the way to low cost and efficient production of ethanol. Once such technical barriers are surmounted and ethanol production can be combined with the efficient electricity production from the unconverted wood fractions like the lignin, the ethanol cost would come close to the current gasoline prices and the overall system efficiencies could go up to about 70%. Though the technology to make this an economically viable option still does not exist, promising technologies are in the works and there are currently a number of pilot and demonstration projects starting up. The fuel extraction process from the algae. One strategy is to utilize the microalgae grown in the water. The single cellular photosynthetic plants from the 10 to the power 6 meter to the 10 to the power minus 4 meter in diameter. They grow rapidly, generally doubling the numbers within 24 hours, and some species contain whales, as do larger plants. Whale content ranges from the 15 to 75% dry weight. Consequently, potential annual whale production from whale-rich microalgae is 50,000 to the 1,50,000 L per HA, which is the 10 times more per unit area than from the vegetable source. Commercial growth is usually in open ponds at the 20 degree centigrade to the 30 degree centigrade with the input of the sunlight, carbon dioxide and the nutrients. Biodiesel from the algae is sometimes referred to as the second generation of the biofuel. The algae comes from the stagnant ponds as shown in the figure in the natural world, and more recently in algae farms, which is described in the figure, which produce the plant for the specific purpose of the creating biofuel. Each fiberglass bioreactor has an operating volume of 10 cubic meters of water and is operated as an air mixed flow through vessels. Nutrient-rich wastewater inflows are pumped in through the clear plastic hose, that is blue clamp, and these are the blue clamps, and the water outflow occurs through the white plastic pipe shown in the figure at the water line. These bioreactors are intended to be operated year-round as the temperature of the inflowing wastewater is consistently 8 to 10 degrees centigrade. Advantage of the algae fuel extraction on the following: no carbon dioxide back into the air, self-generating biomass. Algae can produce up to 300 times more well per acre than the conventional crops. Among other uses, the algae have been used experimentally as a new form of green jet fuel designed for the commercial travel. At the moment, the upfront cost of the producing biofuel from algae on a mass scale are in the process but are not yet commercially viable. Challenges: in open ponds, the well-bearing microalgae becomes contaminated by the local algae and bacteria, so the transparent enclosures are needed. Second source of the fuel extraction is the carbohydrate. From the carbohydrate or the sugar-rich biomaterial. It comes from the fermentation of the starches derived from the agricultural products like corn, sugarcane, wheat, beets and other existing food crops, or from the inedible cellulose from the same. The produce from the existing crops can be used in an existing gasoline engine, making it a logical transition from the petroleum. It used in auto industry, heating buildings, flowless fireplaces. At present, the transportation cost required to transport the grains from the harvesting to processing and then out to the vendors results in a very small net gain in the sustainability stakes. Third one is the from well-rich crops and vegetables. It comes from the existing food crops like the rapeseed, sunflower, corn and others after it has been used for the other purposes such that the food preparation like the washed vegetable oil or the WVO or even in the fast use form, straight vegetable oil or SBO. Not susceptible to the microbial degradation, high availability, reused material. It is used in the creation of the biodiesel fuel for automobiles, home heating, and experimentally as a pure fuel itself. At present, the WVO or the SVO is not recognized as a mainstream fuel for the automobiles. Also, WVO or the SVO are susceptible to low temperatures, making them unusable in colder climates. From the well-rich crops and vegetables, the vegetable soils are extracted from the biomass or a substantial scale for use in the soap making, other chemical processes, and in more refined form for cooking. Categories of the suitable materials are as follows. Number 1, seeds like the sunflower, rapeseed, jatropha, soybeans, etc. Nuts just like whale palm, coconut, copra, etc. 50% of the dry mass of the whale. Example as the Philippines annual production of the coconut whale is 1.5 million. Third is the fruits, example of the world olive production. 4 is the leaves, just like eucalyptus leaves. From the tapped exudates like rubber, latex or the jojoba tree oil. 6 byproducts of the harvested biomass, for instance the oil and the solvents to the 50% of the plant dry mass. Turpentine, oleoresins from the pine trees, oil from the euphorbia. From the agricultural waste or the organic or the inorganic sources, it comes from the agricultural waste which is concentrated into the charcoal like biomass by heating it. Very little processing required. Low technology naturally holds carbon dioxide rather than releasing it into the air. Primarily the biochar has been used as a means to enrich the soil by keeping the carbon dioxide in it and not into the air. As fuel, the off gases have been used in the home heating. There is controversy surrounding the amount of acreage it would take to make the fuel production based on the biochar viable on a meaningful scale. Furthermore, use of the agriculture waste which is rich with the inorganic elements as compost fertilizer in the agriculture. Now come to the biodiesel. The biodiesel is a clean burning diesel fuel produced from the vegetable oils, animals, fats or grease. Its chemical structure is that of the fatty acid alkaline esters. Biodiesel as a fuel gives much lower toxic air emissions than the fossil diesel. In addition, it gives the cleaner burning and has the less sulfur content and thus reducing the emissions. Because of its origin from the renewable resources, it is more likely that it competes with the petroleum products in the future. To use the biodiesel as a fuel, it should be mixed with the petroleum diesel fuel to create a biodiesel blended fuel. Biodiesel refers to the pure fuel before blending. Commercially, the biodiesel is produced by the transesterification of the triglycerides, which are the main ingredients of the biological origin wells, in the presence of an alcohol such that the methanol or ethanol and a catalyst like the alkali acid or enzyme with the glycerin as a major byproduct. After the reaction, the glycerin is separated by settling or centrifuging, and the layer obtained is purified prior to the using it for its traditional applications like pharmaceutical, cosmetics and the food industries, or for the recently developed applications like the animal feed, carbon feedstock in fermentations, polymers, surfactants, intermediates and the lubricants. However, one of the most serious obstacles to use the biodiesel as an alternative fuel is the complicated and costly purification processes involved in its production. Therefore, the biodiesel must be purified before being used as a fuel in order to fulfill the EN 24214 and ASTM D6751 standard specifications. Otherwise, the methyl esters formed cannot be classified as the biodiesel. The European biodiesel specification EN 14214 is more restrictive and applies only to the monoalkyl esters made with the methanol, fatty acid, methyl ester, FEM. The minimum ester content is specified at 96.5%. The addition of the components that are not fatty acid methyl esters other than additives is not allowed. The US specification as the ASTM D6751 defines the biodiesel as the monoalkyl esters of the long chain fatty acid derived from the vegetable oils and the animal fats. Removing the glycerin from the biodiesel is important since the glycerin content is one of the most significant precursors of the biodiesel quality. The biodiesel content of the glycerin can be in the form of free glycerin or the bound glycerin in the form of glycerides. The total glycerin, which is the sum of the free glycerin and the bound glycerin. Severe consequences may result due to the high content of the free and the total glycerin, such as the buildup in fuel tanks, clogged fuel systems, injector fouling and the valve deposits. Now come to the one-step trans-esterification. The esterification process is straightforward for those with the basic chemical knowledge and with the due regard for the safety can be undertaken as a small batch process. Continuous commercial production obviously needs more sophistication and uses the whatever well is most readily and cheaply available in the country concerned, just like rapeseed well in the Europe, called the canola in some other countries, and the soya well in USA. The biodiesel can also be made from the waste, the cooking well, and from the animal fat, which I described earlier. For the synthesis of the biodiesel, the following materials are used: the well sample like the FFM, SD and BSD, methanol marked 90%, and the potassium hydroxide as a catalyst. Methanol and potassium hydroxide were premixed to prepare the potassium methoxide and then added to the well in the reactor. This is the well, which is mixing speed of the 400 rpm for 2 hours at 50 degrees centigrade. The molar ratio of the well to the methanol was 1:10. Finally, the mixture was left overnight to settle, forming the two layers. These are the two layers, namely the biodiesel phase, this is the upper layer, and the glycerin rich phase, this is the lower layer. Basically, the methanol was the alcohol of choice and the KOH was used as the catalyst. Potassium methoxide solution was prepared freshly by mixing the predetermined amount of methanol with the KOH in a container until the all catalysts are dissolved. The PMS was then added to the 200 gram of oil and stirred vigorously for 30 minutes at the 30 degrees centigrade. Then after the mixture was carefully transferred to a separating funnel and allowed to stand for 4 hours, the lower layer glycerol, methanol and most of the catalyst was drained out. The upper layer, that is the methyl ester, some methanol and traces of the catalyst was transferred into the another flask containing freshly prepared PMS mixed at 60 rpm under the reflux at the 60 degrees centigrade for 30 minutes. Afterwards, the mixture was carefully transferred to a separating funnel and allowed to stand there overnight. The glycerol was removed by gravity settling, whereas the obtained crude esters layer was transferred into the water bath to remove the excess methanol at 65 degrees centigrade and 20 kilopascal pressure. The obtained crude methyl ester were then cleaned thoroughly by filtration by washing with the warm 50 degrees centigrade deionized water, dried over the anhydrous Na2SO4, wetted and applied for the further analysis. Now the comparison of the direct combustion, anaerobic digestion, fermentation, well extraction, pyrolysis and gasification. From the direct conversion, we get the heat and the electricity. From the anaerobic digestion, we get the heat, electricity and the gas. From the fermentation, we only get the bioliquids as the biofuel. From the well extraction, we get only the biofuel in liquid phase. From the pyrolysis, we get all about the heat, electricity, gas, liquid and the solids. From the gasification, we get the heat, electricity, generate the biogas, biofuel. From the annual crops, that is the grassy crops, well seed crops, we will get the well, protein, sugar. Grassy crops, we will get only the sugar and the lignocellulose. The chemical characterization of the different biomass sources. The perennial crops, just like the grassy crops, well tree crops and the lignocellulosic tree crops. The residues and the waste, the sources are green waste, animal waste and the organic fraction urban waste. These are the process technologies from where we will get the well and the lignocellulose. Anaerobic digestion for the fats and the proteins and the sugars and the cellulose. For the pyrolysis, the source is the well and the protein, the sugar and the lignocellulose. These are the comparison between the technologies for the energy conversion biomass, the possible scale, the feedstock flexibility, the conversion efficiency, the output flexibility, market value of the product and the development status. For the direct combustion, the feedstock flexibility is high, conversion efficiency is low, market value is low. For anaerobic digestion, the feedstock is medium, conversion efficiency is medium, the output flexibility is low, market value is medium. From the fermentation, the feedstock is medium, the conversion efficiency is medium, the output flexibility is low, the market value product is high. For the esterification, the feedstock is low, the conversion efficiency is high, the output flexibility is low, and the market value is medium. For the esterification, the market value is very high. So from where we will get the biofuel. From the pyrolysis, the feedstock is high, the conversion efficiency is medium, the output flexibility is high, market value is medium. From the gasification, all are the mediums. The fuel is the solid, either the 100% biodiesel or the blended with the petroleum based diesel. Although the production cost of the biodiesel substantially exceeds that of the conventional diesel fossil fuel, such the governments justified the policy in terms of the external benefits for the environment. The energy density of the biodiesel as an ester varies with the composition and is typically about 38 megajoule per kg, which is greater than for the raw oil and near to the petroleum based diesel fuel at about 46 megajoule per kg. Nevertheless, in practice, the fuel consumption per unit volume of a diesel engine vehicle running on biodiesel is little different from that of the fossil diesel. The quality standards have been established for the compatibility of the biodiesel with the most vehicles. The minor benefit of the using biodiesel is that the exhaust smell is the reminiscent of the cooking. That's all of the biomass energy sources. These are the references from which you will get more knowledges. Thank you.